Good afternoon, everyone. My name is Andrea. Today we are going to speak about piped water supply network based on the software Epanet. Why I choose to do this workshop or webinar is because in Syria, currently we are doing mainly water trucking, but very soon, on the longer term, we will be obliged to connect those IDP sites into existing water network system, or we will have to develop water network system based on new borehole. On the long term, as you know, water trucking is not sustainable at all. It is very expensive. The idea is that you understand the basic on hydraulic for water supply network. The idea is that you understand what you have to consider before developing a network while you are running the network and during the simulation what you need to do. Of course, you are going to get used to this software, but at the end, you are not going to be the expert on water supply network. It should be the beginning for you to understand, but then further learning from your side is necessary. This workshop is going to be split in two parts. Today, the first part, and the next week, on Monday, the second part. Today, we are going to have an overview on the basic hydraulic rules, why you do a network, and then we are going to develop a very simple network, but it will not be finished. The next week, we are going to run the network over time, doing a time analysis. Let's start with Epanet. Epanet is an open source software that simulates water supply system in pressurized pipe network. It means the pipes need to have water all the time. They must be under pressure. It is the difference between open channel, which are used for drainage. This software simulate or reproduce the behavior of the network, but it will not tell you exactly what type of pipe do you need. It will tell you only if the pipe that, or if the pump, or if the tank that you have chosen is good or not good. So then you have to change the size of the pipe, for example, and then it will tell you again, yes, it's good or not good. It's not a software that will advise you to use a certain type of pipe. It's a very old software. It is done 2003, so it's not at all user-friendly. There was a second version, version 2, 2008, but after that time, there was no major development. There are apparently currently trying to do a new version of it, but they are not presenting anything. With that, I want to say that there are many other alternatives to Epanet. Here we have a list of the main software that can do the same as Epanet. Some of them, the best one, are commercial as well, very expensive. Maybe just one name on this one, WhatThis. WhatThis is actually like Epanet, but a little bit more user-friendly. To be honest, I've never used WhatThis, but what I know is that it's very compatible to Epanet. So in case that you want to understand better Epanet, it might be a good idea to check as well WhatThis. You can find WhatThis. You can find WhatThis on internet. You Google it and you download it. So we are going to work with Epanet and this time. So before you start to work with Epanet, we have to understand the difference between an existing network and a new network. If you do a new network, the good thing is that everything is new, so you can plan properly. You know exactly what type of pipe you can use. You know exactly what type of pump you can buy or you have to buy. But what you don't know is how people will react on the network. As far as I know, for Syria, this shouldn't be a problem because Syria people are used to network, but this is more a problem for developing countries like in Africa. You do not know if people really accept piped network. You have no idea if the community is ready to invest time to the maintenance of the network. And on the longer term, the sustainability of the network is a not known issue. And but on the other hand, if you have an existing network that has to be rehabilitated, so you know how the population react on the network, but what you don't know is the quality of the network. You don't know what type of pipe you have in it, the size of the pipe. You don't know how many, let's say, illegal connection you have. And so it is a very different approach. In our case, we are going to work on a new network because we plan to do this network on our IDP site. But anyway, before you do a network, you have to think about the sustainability of the network. The network, even if it's a gravity network, need to be maintained. And for that, you need skilled people and you need some money. As well, a network needs to have access to everyone and on the same level. If you don't have access, if you don't give access to all the people, you will have the situation on the picture on the right, where you will have many illegal connections. And additionally, if you do a new network, you have to plan in advance about the development of your sites. If you size your network for 1,000 people, you have to calculate that the network would last for 20, even more years, and the population might increase accordingly. Therefore, you should calculate or size your network considering the development of the area. Where you should do a network, you should do a network when you have a concentration of people. In some cases, you have few. There is a child crying in behind. Maybe we can, Randa, I mute you. If you if you want to do a network where you have a scattered population, this will be complicated because you will have many meters of pipes, and no one is going to maintain those pipes. And you need also for a network social cohesion, a population that lives together and wants to live together. For our IDP site in Syria, that's the case. I think for Syria, on the longer term, you need to have a water supply network. Okay, of course, network should improve the situation, and therefore it has to be built properly. So we need to avoid the technical problem. It means we need skilled people. You see on the picture on the right, if you have strong leakages, you might have an environmental problem. The topography should as well allow network and trying to minimize pumping cost. In flat area, networks are expensive because we have to raise the water to the elevation tank. And yeah. Okay. And of course, at the end, those networks are usually built through donors. And that's why we should have a proper calculation of our network. We should have a proper projection of the network because we are also responsible in front of the donors. We do not want to have a bad project. We want to show that our network is sustainable and as well on the long term. The network must be extendable. The material need to be selected in a way that it is economical, correct, and the right size. Okay, now let's go to the network first, sorry, to the software first. So like I told you, Epanet is free. I've sent previously the link where you can download it. Please try to download the last version, which is 2.2. There are as well manuals and books. I have given as well the books. Those books, the link of those books that I have given are very good. And if you take the time to read all those books, you are going to be a specialist. So what are the limitations of Epanet? Like I've told you, Epanet will tell you if our chosen pipe is good or not, if the chosen diameters is good or not for the plant network. Epanet will help you to extend the network and see if the extension can be supported by the existing network. Epanet will help you to size the tank, the valves, and the pump. Will help you to select the pump. And additional also is going to show you how the chlorine or the clarification of the water will proceed, but we are not going to enter in chlorination in this workshop. Okay, but what cannot do Epanet? Epanet cannot simulate open channel. It cannot simulate drainage, and as well, it cannot simulate change in the water supply. Sudden change like closing and opening a valve causing the water hammer. This you cannot simulate. For that you have other type of software. It cannot evaluate if you have mud or air in the pipe, and that's it. And also it cannot, like I was telling you, it cannot tell you how this network behave if you suddenly change the water demand. That's why we will see next week, for time behavior of the network, we will have to create a time pattern. This is the topic of next week. So to understand how the network and how Epanet works, there are main elements to be considered and to keep always in mind. The first element is the elevation of the water or of the tank or the pipes or the joints. Elevation can be actually put as the energy of the network of the water. Then you have the pressure. I don't have to explain what is the pressure in the water. Everyone knows what is pressure. Is the meter of water that you have above. Then you have the velocity of the water in the pipe. We have the water demand. It means how much water is requested at the tap stand or at the fountains or at the house connection. Then there is the water availability, how much water is available for the network. It could be at the source, it could be a borehole, it could be a spring. And then there are components of the network, which are pipes, pumps, reservoir, valves, and tanks. As you see, we have only 5 elements and actually few elements. So let's speak about the first very important hydraulic consideration. I don't know if all the participants are engineers. That's why I go through these elements very quick. I'm sorry for that, for those people who knows what I'm speaking about. But I think it's very important to understand that the same amount of water on a big flowing on a big pipe has a lower velocity compared to the same amount of water flowing in a small pipe. So the Q stay always constant in a pipe, but the speed, the velocity of the water might change. And we will see now that the speed for a water supplied network is a very important parameter to consider. Here you see 3 formulas. You don't have to learn these 3 formulas, but you have to know that Epanet works on those 3 formulas. But Shizi Manning, it's actually a formula that is used for open channel, so you shouldn't consider that form. But you have to choose when you set up your Epanet software between Hazen and Williams and Darcy and Weisbach. Both are good and both have a common items. If you see, you have the velocity exponential for the calculation of the friction loss. Friction loss is actually the loss of energy that is dissipated in a pipe when the water flows. And if you see, the friction loss along pipes is always on a exponential of the speed. What does it mean? It means if I have water in a pipe flowing at 1 meter per second, I have an amount of friction loss, let's say 1. If I have the water flowing double so quick, 2 meter per second, my friction loss, it is actually 4 times more. So the friction loss is exponential to the velocity of the water in the pipe. That's why velocity in the pipe is an essential parameter that you should consider when you develop a network. And the velocity on a pipe should not exceed 2 meters per second unless you need to dissipate energy. If you have too much energy, if your tank is too high, for example, then it might be a good idea to have a very high velocity in the pipe in order to dissipate energy along the pipe. Depending on which formula you choose, you have also to...
Andre, I apologize. If the tank is higher,
Yes?
what I missed what you said after that. I apologize.
So if you have a very high tank, let's say in a mountain, it means your water will have a very high amount of energy, potential energy. We are going to speak about that later. So at the tap stand, you are not allowed to have too much energy because you might destroy the pipe, you might destroy the tap, and if not, the water will spit out of the tap too quick. So that's why you might need to decrease the energy of the water, and one way to do that is to decrease the size of the pipe. In doing that, the speed will dramatically increase and the friction loss as well will increase exponentially. Another way to decrease the energy is with energy reduction valves. So whenever you set up your Epanet, we will see later, you have to choose between the three formula. Yes, please. Whenever you set up your Epanet program, you have to choose between the three valves, the three formula. Like I've told you, Chassis Manning, do not consider it, but you can choose between the two. And depending on what you choose, you have to choose the constant for the coefficient for the rawness of the friction loss. If you choose Hazen and Williams, and for example, you have plastic pipe, PE pipe, you choose between 140 and 150. If you have Darcy and Weisbach, you have other numbers to choose. This is important not to mix up the coefficients. We will see later. Now we have the Bernoulli equation, which is also extremely important in a water supply network. In short, this will say that the energy that you have at the beginning of the system, it is similar to the energy that you have at the end of the system plus the friction losses. And we have three types of energy in a pipe network. We have the elevation, it means the meter above ground, let's say an elevated tank. We have the pressure, the meter of the column of the water above the, let's say, the outlet, and then you have the speed of the pipe of the water. All the three together gives the energy of the system, which should be constant over the network, plus the friction losses. This is very important to keep in mind. Okay, now before starting to draw a network, we should also see what type of network we have. We have principally two types of network. We have a branched network, and you can see in the drawing, it's just a line, and it is good, but if one of the pipes breaks down for some reason, the rest of the network is jeopardized. And then you have the looped network. The loop network make a loop, and this is actually better in terms of stability, because if one pipe breaks down, the system will still receive the water, but on the other end, it is more expensive because you have more meter of pipe. Not all, in some cases, if the network is very simple, you might go for a branched network, but if you are in a city or in a complex IDP situation, it is advised to use a looped network. Like I was telling, Epanet works with 6 main objects. It is few objects, and that's not very difficult to keep in mind. We have the junction. A junction, it's a point. We have the reservoir. Reservoir, here it meant like a lake, like a borehole. It is meant the place where the water is coming from. A reservoir has a constant elevation. We have the tank. Tank is a closed tank, can be elevated tank, can be a bladder, can be a rotor tank, something that has variable elevation. When it's empty, is low. When it's full, is high. Then we have the pipe. Pipe are characterized by size and length. And we have the pumps. Everyone knows what is the pumps. And then finally, we have the valves. Let's now check the characteristic of each component. The junction. Junction is a point that has a specific height. A junction can be a tap stand, for example. In that case, you have to give to the junction the demand. A junction can also be a change of slope without any type of demand. A junction can be a place where you put a valves, for example. In a junction, you can even have water coming in. In that case, it would have a negative demand. That's it. So the main element for the junction are elevation and demand. Then you have the reservoir. Again, the reservoir, don't mix it with the tank. It's the place where we take the water from. It can be a lake, it can be a borehole or a river. If a river, okay. The thing is that the reservoir has a constant elevation and reservoir has always water. There is no way that you empty the lake, for example, or that you empty the borehole. In Epanet, in reality, yes, you can dry a borehole, but an Epanet reservoir has always water. So the main element of the reservoir is the elevation. Then we have the tank, like in the picture, is a closed tank. Tank has several type of elevation. So the bottom, the maximal elevation, the minimal water level. These 3 elevation we have to give in the system. You have to consider that Epanet use only round tanks. Even if in the reality it's a bladder or if it is a square tanks, in Epanet it is round. So you have to calculate back the size or the volume of the tank into a round tank. Once you have the volume, it is easy to go back to the round count because the parameter that are used is the radius, elevation, initial level and maximum level and minimum level. Tank can be overflow and or can be empty. If it's overflows or it is empty, Epanet will give you an error because we're not supposed to overflow tanks or to keep tanks empty. Then we have the pipes. Pipes are actually put between 2 junctions. Pipes doesn't have an elevation because the elevation is given by the junctions. But pipes has the length, yes, and the internal diameter. Even here, you have to be carefully because the internal diameter of the pipes change also in relation to the supported pressure. So the best thing to do is to go to the supplier to check the catalog to see what type of pipes do they sell, and then to be precise on the internal diameter of the pipes. And of course, pipe have a friction factor, and this depends on the material of the pipe. You have PE, plastic pipes, concrete pipes, iron pipe, galvanized pipe, many type of pipes. And you should know in advance which type of pipe you would like to have for your network, because this parameter has to be inserted in the Epanet. The issue of the pipe is when the pipe is old, because you don't know the quality of the pipe. So at the very beginning, they might be clean and smooth, but on the longer term, there might be incrustation, there might be erosion or corrosion, depending on the pH. And this type of changement of the material of the pipe reflect on the friction of the pipe. But it's very difficult to quantify that. So like I was telling you, the parameter for the pipes is start node, end node, length, diameter, internal diameter, and the constant roughness element, depending on the material. And then you have the pumps. The pumps in Epanet are inserted between two junctions. It's not to consider like a junction. It's just between two junctions you insert the pump. It means the main parameter of the pumps are start node, end node, and pump curve. I think everyone knows what is a pump curve. If not, it's actually the capacity of the pump to lift water, to lift a certain amount of water over a certain elevation. Each pump arrives with the pump curves. Okay, and then you have the valves. You have in Epanet 6 type of valves, but I advise you for our purpose not to use the valve, not because it's not good to have valves in a network, but for small network in a country like Syria, where the maintenance is anyway a difficult issue, it's better to avoid valves, because those valves, first of all, they are extremely expensive, and then the maintenance of those valves is not assured. We can have, yes, a gate valve, this for sure, but special valves like pressure reducing valve or throttle valve, maybe it's better not. It's better to avoid this type of valves. But anyway, Epanet gives you the possibility to introduce valves in the network. And then the driving the network. Once now we have seen the 5 elements, and now it's time to drive to draw the network. First of all, of course, you need to have a map of your system. You need to know where is your water supply, where is your lake or your reservoir. You need to know where you want to put your tank, your elevated tank, and you need to know where you want to put your top stand or your connection to the households. For that, you need a map, GIS, for example, but even AutoCAD could be a solution. But if you have GIS, and like we have seen previously, with Global Mapper, for example, it's easier to get the elevation of those items and to get the length of those items. In Epanet itself, there is no need to draw precisely if you switch off the automatic length, because by each pipe and by each element you give the parameter manually. If you switch on the automatic length, then you should draw precisely and you should draw in scale. We are not going to see how to work in scale, but if the request is there, we might do on the future that. Another thing that you should consider in Epanet is that, considering that it's an old software, it doesn't have the undo option. It means if you change a pipe, you cannot say, oh, no, I don't like this pipe or this new size, I go back. No, you lose the old setting. So what does it mean? For every changement of the network, you have to save the file and somehow in a paper write down what you have changed, because you cannot go back like any other Windows document. It is actually not very practical. And like I was telling you, Epanet is not going to tell you which one is it's not going to propose you a pipe. It's just going to tell you this pipe is good or this pipe is not good. And that's why you have to remember when you make a change. That's why you have to say, you do several trials up to the moment where your network is fine for you. Okay, now we go and we start with a very simple network with Epanet. I don't know if you have Epanet open on your computer or not, but anyway, you have the presentation, and later with calm, you can go through the presentation step by step and check what I'm going to say and redo it. Before starting drawing the network, you have to put some default label. So first of all, you go to you open Epanet, and you go to project and default. Here you have three, let's say, type of properties, the ID labels. I advise you to give a label to each of the elements. For example, the junction, you give J, reservoir, you give R, tanks, you give T, and pipes P, pumps P, and valves VA. Doing like that, when you add, let's say, a pipe, it will add PI1, PI2, PI3. If you don't put a prefix, it will just be the number, and then you might mix up pipe with pumps or pipe with reservoir because there is no prefix. So it's better to do the default, and then finally also save the system as default for all the project. Below you see the option to save it as default. Then you go to the properties. Those are figures that appears when you open or when you create a new element. Let's say I create a new tank. If I write 2.5, it means the new tank height will be 2.5, but you can change it. So anyway, these figures you change every time, but for example, for the pipe roughness, you write 140. If the whole system is PE, maybe 140 is good for all the pipes, and you don't have to change it anymore. And also important that you switch off the auto length so that you can draw your network free and you don't have to be too much precise. Then also you have the option to choose the unit that you work on. You can use the metric units or the imperial units. I like to work with liter per second, but you will see you have several options. You can work with cubic meter per hour, on cubic meter per minute, liter per minute, as you wish, as you feel more comfortable. Just remember the unit that you have chosen, because this has to be after interpreted. And then also you have to choose the head formula. Like I was telling you, there are actually two head formula to choose. Asana Williams HW is that one what I use. That's why also I was use 140 as a roughness parameters. The rest of the parameters are not really important at this level. You can keep it like they are, but still remember to save your default for all the new project. And then you start to draw your network. Okay, like I was telling you, you need to identify on your GIS or on your AutoCAD where you have your spring, your borehole, or your water treatment plant. You might even have an existing network as a start for your new network. But what you need definitely is the elevation of this point. You need to know if a pump is requested or not. If it is by gravity, which is hopefully like that because it's cheaper. You don't need any pumps, but in most of the cases you need a pump. Then you should also have an option or several options of pumps available. You can find them in internet, on the market. You can see what you can find. So you need the pump curve. And then you need the location of your nodes of the junction. Like I was telling you, the junction are actually the points where you have a demand. It can be a connection to a house. It can be a tap stand. It can be a secondary tank, somewhere where the water is coming out, but as well a junction could be a valve or a changement of the slope. When I speak about a valve, because you might have a pipe going up to a hills and coming back, in order to avoid hair in the pipe, you should put on the highest point an hair valve or a system to take out the hair. That's why you might put a junction there without any demand. Then you need the pipes, you need the location, it means the start node and end node, and the length. The length, you take it out of GIS or AutoCAD. And then you need a tank. Here I wrote reservoir, but it's actually a tank, is wrong. Again, you need the elevation of the tank. And then, very important, you need the water demand at the junction. And the water demand depends, of course, on the amount of people that are using the water and the quantity of water that those people use per day. You might refer on standard, but we know in Syria, sphere standards are not good, they are not adapted. So as far as I remember, we work with 50 liter per second, 50 liter per day and person. In some cases, you might have agricultural land, you might have cattle. So those are also figures that you need to consider. But for our cases, probably 50 liter per day per person is good. So it means we need to know how many people relay to this water point, to the tap stand, for example, and then you can determine the water demand. And then you put all those figures on an Excel sheet, like you can see here. So in this case, we have 4 settlements with 4 tap stand, let's say, and each settlement or each part of the site has a number of families with some people, and then you consider the water demand per day for each junction, for each tap stand. You divide this water demand by 24, so you have the water per hour, and then you divide per 3,600, and then you have the liter per second. This is not a real value, but you start like that because assuming that you will have a constant flow during the day, you would need this type of amount of water. In reality, you will see later, it's not like that because we have the time pattern. People are going to take the water in the morning, at lunchtime, in the evening, and not at night. But this is a topic of next week. So you have your Excel file where you have described all the junction. You have the elevation of all the junction for each settlement number of people and water demand in liter per second if you choose liter per second. Then you have the tank. Again, you need the elevation of the tank. Tank can be existing. In that case, you need to give the real dimension of the tank, or maybe the tank is new, so you have to estimate at the beginning how big should be the tank. It can be that you have already a tank in the storage, Oxfam tank, or maybe bladders. depending what you have, you might have already the dimension, or you might have to construct the tank for that. And then you have the borehole or the source, called in that case a reservoir, the lake to be clear. And for that you just need the elevation. And then you have to choose a pump. Even that, the pumps depends on the elevation that water has to be pumped, and then on the quantity of water that have to be pumped. The thing is that if you want to pump all the water for one day in a short time, you need a big pump and a big tank. If you want to pump the water over many hours, you might need a smaller pump and a smaller reservoir. This is a fine tuning that we are going to see later when we do time analysis. And then you will have the pipes. Pipes are, like I was already saying, put between joints, and the distance is fixed depending on your map. It might be a good idea to do for each pipe a section to see if there are elevated points where you might need an air valve, but for a small network probably is even not necessary. Even that, you write down on your Excel file the pipes, the meter of the pipes from where to where. This is the base when you start to develop your network. Okay, now you open your Epanet, and what you do as a first, you upload in your Epanet your backdrop map. So it's a map that you have previously developed in AutoCAD or GIS, and this is important so that you have a background and you can draw your network somehow realistic. This will help you to not get lost. Once you run the analysis, you will have problems, you will have errors, and then graphically you will identify the error. If you have a backdrop map which corresponds to the reality, it is easier to identify the errors. Important again to assure that your auto length is off. And you can see it on the bottom left, if it's on or off. And as well, on the bottom left, you see if you work on liter per second or cubic meter per minute or gallons per
I'm
hour.
sorry, Andrea.
Yes.
I'm sorry, Andrea.
Yes.
Down on the left, what needs to be on? I'm sorry, I missed that.
Yes, the auto length must be on. Off, sorry, off.
Okay, thank you.
Yes.
Thanks.
If it's on, and if you draw the pipe, the length of the pipe will be automatically calculated, but it might not be right. So you keep it off and then you put the length manually for each pipe. Be aware that your map is just a support, a help for you, but it's not georeferenced. Okay, now how you can make such a map? Like I told you, it's GIS, for example, or AutoCAD. The thing is that you have to export this map as a picture, vector picture, and the best extension for that is EMF. Doing like that, with this extension, it is a rasterized picture, and your resolution is better when you zoom in. And any picture elaborating software will have the option to save with this extension. Okay, now let's start. Let's assume we manage to upload in our Epanet our background map. This is like that. So we have to start now adding our elements. Like I told you, only 5 elements, and better only 4 because we are not going to put any type of valves. So you have to start. You cannot start with a pipe because pipes are between junctions. So let's start with the reservoir, with the spring or with the lake or yes, or
Sorry, Mr. Edward, just a minute. Do you mean that we have to put this map as a picture, take it from Google, yani?
you can take it from Google Earth, you can take it from wherever you want. The thing is that it is easier to have a background map. How you do the background map is up to you.
Yeah, but in this case, it will not be to scale. It's not a
The,
scale.
I mean, yes, the picture is on scale, but it's not geo-referenced.
Ah, okay. Thank
It's
you.
not geo-referenced, but it's on scale. But if you have auto length on, it will not be on scale. So auto
So,
length must be off, and then you put the length of the pipe yourself
so it will be as a reference, yani.
as a reference only.
Thank you.
Yes, it's much easier.
Thank you.
Theoretically, you could do it without map. That's not a problem, but it will be more complicated to understand the error if you do it without map. Okay, so again,
Thank you.
you develop your background map with GIS ideally, and when you do your background map, do not use, let's say, imagery behind, because what you need is just to know where are your junction, reservoir, tank, and pipes, and you don't need too many information on this background map. And as well, when you do your background map, you have to um, activate the name of the junction, the name of the pipes, the name of the tank, the name of the reservoir, so that when you insert it, you can type the right name as in your Excel file, so you don't mix up the elements. So in AutoCAD, in GIS, it's easy to display the names. In AutoCAD, it's also easy, but maybe a little bit more complicated, at least for me. So let's start with the network. Now we have an empty Epanet file with a background map taken from GIS. This is a picture of, this is done with Quantum GIS. I insert it and I add the reservoir. Let me see if, okay. So the reservoir, now I see the reservoir is actually this icon here. You can see my mouse, I hope. I don't know why it's wrong, but here is the reservoir. You just click on the reservoir and you put it there. And you click, then you continue. You can eventually, with this icon, zoom in. And then you click on the right side, you will have the browser. You can see on the right side of Epanet, you will have the browser under data. Automatically, the reservoir information will appear, since we have given to the reservoir a prefix R. The first reservoir will receive the name R1. You click twice on this R1, and then you will see the information, the parameters of the reservoir. The name is R1. You can change it if you want. The coordinates, don't care about that because the system is not geo-reference. You might write a description, up to you. Here you have to give the total head, and this is the elevation of the bottom of the reservoir, the minimum acceptable water level. So the bottom of the reservoir, and the rest you leave it like that. Like I told you, a reservoir also only requires one parameter, which is the elevation. If your reservoir is a borehole, you need to consider the dynamic water level. And this is very important. Now, I don't know how is behaving the groundwater in Syria, but in some cases you might have even more than 50-meter drop down in a borehole. And 50 meter is a lot of meter. That's why you need to do a pump test if you have a borehole to identify the dynamic water level, and this is the elevation that you give on the parameters for the reservoir. Very important. Then Next point would be we put the junction. In this drawing, we have 1, 2, 3, 4, 5 junction. This junction is actually only a change of slope, but there is no demand. Can you see my mouse? I hope. This is a junction where you have one water demand, junction where you have another water demand, junction with water demand, and junction with water demand. Like I've told you, it's a very simple network, but it makes sense to work at the beginning with the simple network. So for the junction, you need to choose this icon here, just which is here. You take it and you put one here. No, let's say junction 1, I don't know where it is. Okay, 1, 2, 3, 4, and 5. Okay, you can see where I have put the junction. And then each junction will receive a name, junction 1, junction 2, 3, 4, 5. And important for the junction, maybe a description. Junction 1 will gives water to the settlement 2. Description, anyway, it's free. It's not important. Important is that you have the elevation of the junction. This is extremely important. And the base demand. If I go back to my Excel work, oh, sorry, I'm going the wrong direction. The demand, you take it from here. The junction, you have so many family, so many liters per second during one day. This is the demand. And as well, you take the elevation. The elevation you can take ideally from the total station, but you might not have it. So on the worst case, you take it from the digital elevation model as RTM, knowing that is not precise. But ideally, the elevation, you make an assessment, a survey with a total station with a drone. So here you see, again, the same system, you have here the data on the right. You click on junction 1 and then, or junction 4, and then, sorry, and then this will appears and you give the parameters. Name you can change. Elevation you give out manually, and base demand. That's all what you need for the junction. Again, if there is no demand, this is 0. If water is going in, the demand is negative. Let's continue. Then, yes, for the elevation of the junction, what you will have from your map is the elevation of the ground point. But be carefully, because sometime you might have a tap stand, which is more or less 1 meter high. So from the ground level, you add 1 meter. But the junction could be as well a connection to a house. And then you have to check how high goes the water into this house. It might be 3 meters, 6 meters, even 10 meters. It might be a health center with an elevated tank on the roof. Then you have to give the elevation of the inlet of the tank. So you have to be carefully and check physically every junction, every point of water demand, and identify the right elevation. Okay, and then consider the real height. Yes. And then demand, and the demand, like I was telling you, okay, you have the number of the people, and we know for Syria we calculate 50 liters per person a day, but in other context, the demand might change during the season, it might change during the weeks. And then also the demand change depending on the type of settlement. If some people use to irrigate the area, then you might need more water. If there is some kind of small industry, additionally, you have to consider this demand. Cattle need to be considered. And then in some cases, I don't know, now for Syria, you might consider demand for fire extinguisher. In my country, in Switzerland, we have fixed normative for that. And this is actually the parameter that will influence most of the piping system. In Syria, I don't know. As far as I understood, you don't have fixed prescription for fire demand, but in case you have prescription for fire demand in terms of quantity and pressure, you need to consider those demand as well. And usually for fire demand, this is a very high demand. Okay, now we just with a few words about the sphere standard, but like if I said, it's not that much important for Syria context. Okay, let's put now another parameter, another element. That's the tank, like in the picture, for example. I don't know exactly in Syria how we are going to do the tank, but whatever you do, I repeat, Epanet consider the tank as a round tank, and you have to give the diameter of the tank round. So whatever the volume you consider, you back calculate it into a round tank. Again, you take this icon, you take it and you put it at the location of the tank. You automatically, on your browser on the right, T1 will appear. And if you click on T1, you will have the parameter for the tank. The name, T1, can be changed, of course. The elevation, the bottom elevation. And then here you have the initial level of the water when your analysis starts. How much water is in the tank? It can be 0, it can be 1 meter, 2 meter, depending. But of course, the initial level cannot be higher than the maximum level. And then the minimum level of the tank, of course, is 0 if you really allows you to empty the tank totally. But if you want to keep, let's say, 1 meter of water for fire extinguishing, then you keep just 1 meter. And then diameter. The unit is meter if you are working with liter per second, but you could also have imperial unit if you want. And the rest you don't need. Maybe just coordinates, again, don't take care about the coordinates of the tank. And then finally, we have to put the pump in our case, because we assume that we take the water from a borehole or from a spring, a low, and we pump it up to the reservoir. Like I told you, the pump, even if it looks like a point, is not a point. It's an element that you have to put between two junctions. And one junction can be the reservoir. This can be used as a junction. And the second junction is a kind of fake junction with the same elevation of the pump. So you put a fake junction close to the reservoir, to the spring here, and in between you put the pump with this icon. Be careful that the direction how you draw the pump is important. If you draw the pump from the reservoir into the fake junction, the water is going in this direction. If you draw the pump from the fake junction into the reservoir, the pump pumps on the other side. The direction of drawing is important. Same system, you click on the pump, and on the browser on the right, you will have this visualization. You click twice on the pump, and you have this parameter. The name automatically generated, PU, because it's our prefix. And then you will see the pump link. It's linked between the start node, the reservoir, and the fake junction, junction C6. And that's it, all for the moment. And then, of course, you have also as well insert a fake junction. I go back, sorry, fake junction, this one, which is in reality not existing. The name, you can change it. Elevation, you can put the same elevation as the reservoir. And base demand 0, because in reality, this junction is not existing. Okay, let's continue. The pump like we have done so far, is not working because it doesn't have a pump curve. Now you have to create a pump curve which has to be linked to the pump that you have just inserted. The main parameter for a pump curve is the flow, liter per second, and the height and the head. It is enough that you write here, for example, flow 1 liter and head 70 meter, and you will see the curves is automatically generated. If you have the curves because you have the catalog of your pump, then you can even put all the parameters. You don't have to lose too much time at the beginning with the pump, because during your simulation later you might change the pump curve, you might change the pump. But if you have already a pump in your store and you really want to use this very pump, then yes, then you put the real model of the pump on this moment, so that you oblige or you force your system to work with the existing pump that you have in the store. Of course, you can save the pump curve for further use. And then at this point, you have to link your pump to the pump curve. You open again on your browser under data pump, you click on it, you will have pump curve here. You write 1. I forgot to, sorry, I was jumping. Here, when you do a pump curve, at the very beginning, it's you have to choose curves here, and then you click on this icon, and it will generate a pump curve with the number 1. You see, automatically, you will have a number 1 here. You can either change it if you want, but automatically it will be 1. And then you give the parameter of the pump curve. So that at this point, by the pump information, you give as a reference 1, exactly like your pump curve. It must be the same, because when you run the simulation, the pump will look after the pump curve. If you don't have the same number, it will not, the system will not understand how it is. And of course, you could as well put the power consumption, cost of the power of the kilowatt hour, and then you could also have the cost of the pumping time. This is, if you have those data, why not to do it? This is very helpful when you have to calculate the cost and maintenance of your system. And now it's time to put the the pipes. Like I was telling you, pipes are drawn between 2 junctions. Let's start with the pipes that link the pump with the reservoir. So we take this icon, we click on the junction, and then we go up to the reservoir, up to the next junction, and then you will see the system automatically will snap. The direction of drawing is as well important. When you have water flowing in the same direction that you draw the pipe, the flow will be positive. If the water flows on the other direction, the flow will be negative, but the system will work anyway. Now you have one junction, one pipe. You click on that, pipe 1, twice clicking, and these properties of the pipes will appear. And here manually, you give the length. If you know already what type of pipe you want to use, you just give the diameter of an internal diameter in millimeters of the pipe. If you don't know what type of pipe you want to use, you make estimate the diameter in a way that your speed is between maximum 2 meters per second. Don't use high speed of water in the pipe because of the reason that I was telling before. And then the rawness factor should be 140 already if you have set the default 140. Otherwise, you can change it. Maybe important is to this point, initial status, CV. That's actually the only valve which is included automatically in a pipe. This is the control valves. If it's open, the system will allow to the water to flow in both directions. If it is CV, the water will flow only in one direction. You can keep it open, no problem. Okay. Now just say you, for example, in Switzerland, we have a regulation that says that the minimal diameter of a pipe for water supply is 125 millimeter. This because we have everywhere of our extinguisher which have a very high pressure and very big flows. Syria, it is definitely different, and you know better than I do what type of regulation you have. Okay, now doing like that, we can add the rest of the network. So we have added this pipe. Now we can add this pipe, then this pipe, this pipe, this pipe, this pipe. Always with the same icon here, icon of the pipe. For each pipe, you need to put the information. You change the name if it is not correct already. You have to check that the start node and the end node are correct. Description optional if you want. The length, you take the length from the GIS or from AutoCAD. But this you have to change it manually every time. And the diameter of the pipe, you have to check if the diameter is correct, and that's it. And so now you have your system set, and like I was telling you, you might go to the supplier in Idlib or I don't know in Aleppo, and you might ask what type of pipe do you have. He will tell you I have only PVC, I have only PA of this on this dimension. Important is that you work with the right internal diameter, and additionally you also check the maximal pressure that those pipe can support. Depending on your network, maybe 2.5 bars or 25 meter are enough, but maybe you need more. So be sure that the pipe that you choose resists the expected pressure of the system. And be careful that depending on the pressure, the size, so the internal diameter of the pipes change. Okay, you have now this list. Now you have your pipe, and now you can run the analysis. Most probably you will have to run the analysis, you just click on this here on the Blitz and you run the analysis. Most probably you might have problem. You might have problem for several reasons. Okay. This analysis is actually a single analysis and does not correspond at all to the reality. This is just done to verify that the system is coherent, that all the pipes are connected, that you don't have a single junction somewhere without any connection. But these do not correspond to reality because the demand that we have given is the demand over the full day, so 0.01 liter per second, which is very low amount. But this is important to do because this helps you to identify error in the drawing, in the layout of the system. And it might give an error if, for example, you put at the beginning the level of the water to 0. Then it's like if you start to run the system with no water at the tank. And then, of course, if there is no water at the tank, at the very beginning, no water is flowing down. So you will have a very high negative pressure. So at the very beginning, when you run this first single analysis, put some water in the tank upstairs, 1 meter, for example, And then if you still have errors, check around where are the error. You will get some information, and you have to check all the parameters again until the analysis is successful. Once the analysis is successful, it means that your system is well connected, that hydraulically it makes sense, but still it do not correspond to the reality. At this point, you can see the report. Just going on report and full, you have all the parameters. You have the size of the pipe, you have the length of the pipe, you have the node, the junction, and the demands and everything. And this, okay, can be interesting. Okay. Okay, but now, not today, but next week, because now how time is? Now it's already, yes. For today, it's enough, because next week we are going to use the same background map and the same small network, and we will do a analysis over time. What does it mean? We will run the system considering the demand pattern and the pumping time. We are not pumping 24 hours. Maybe we pump only 3 hours or maybe 6 hours, and the people are not taking the water all on a constant level, but they are taking the water just in the morning, just in the lunchtime or in the evening. And then we will see how the system behaves over 3 days. So we will see the pump running, let's say 6 hours. We will see how the reservoir fills. Then we will see how the reservoir empty. And based on the parameter that we give, we will see if the system is strong, works well, or if there are problems, like, for example, negative pressure. That's it for the first part. While you prepare some question, I just want to show you how it would be in reality if the system works. Yes, I open this very simple analysis. Okay, that's actually my system. Very simple. You run it, it's successful. Now I check the reservoir, for example. I see that I start with 1 meter water. I put 0. I start with 0 meter initial level. I run it, and there are mistakes. Why? Because I run the system without water. Of course, I have here the junction are disconnected, and if I check the pressure on this junction, no, it's here, sorry. If I check the pressure of this junction, junction 2, I check the pressure. I have an extremely negative pressure, so the system doesn't work without water. Okay, but again, I repeat, it is not a real simulation. This is just to check if the system is well connected and just to check if we didn't make any big mistake on the drawing. That's all for the moment. We have more than 1 hour. I'm sorry for that. If you have any question, please do not hesitate. Otherwise, if you don't have question, I invite you for the second part of this webinar on Monday next week. And then,
thank you, Mr. Render. So the program is giving to me only advantage is saying if the system I designed it is running or no, success or no.
At this point.
But it was not designed.
Not designed, but we will do next week the simulation over time, and then the system will tell you if with your parameters the simulation over time works well or not. And if it doesn't work, it will tell you it doesn't work because the tank is too small, for example, because you see it's going to be empty. So it means you are actually demanding too much water from your tank. So it means either you pump more hours or you make a bigger tank. Then you change the parameter and you run the simulation again. And then you have to fine tune your system as long as it works properly. But then you know that the tank that you have chosen and the pumps that you have chosen, the pump time that you have chosen is correct. If it is not correct, there will be an error.
Thank you.
Okay, but this is next week. I don't want to do it today because it will be another hour and then it's too long.
Yeah, it's okay. Thank you.
It's okay?
Thank you.
There is a question here on Mohammed. Does the program include the study water hammer? No. This program do not include water hammer. That's a problem. If you have any question, please do not hesitate to contact me directly or to make any comments on the YouTube channel. There is another question. In a pressurized network, inclination of the pipes towards the exit point increase the speed of water. Not really the inclination of the pipes increase the speed of water, but the difference on elevation. Actually, the elevation of your tank, this is the parameter that gives the energy to the water. And the energy can be translated into speed. And the speed of the water increase depending on the size, internal diameter of the pipe. If you have a very small pipe, a strong pressure, the speed of the water will be very, very high.